Okay, so let me just share my slide. Okay, so today's lecture is on spectrophotometric methods of analysis. So spectrophotometric methods of analysis. So just want to give you almost like a little history. Before the beginning of the 20th century, gravimetry and titrimetry were the analytical methods that were used for quantification of chemical analysis. And accurate results were achieved, but we had some limitations regarding the amount of analytes that could be analyzed, major and minor analytes. That's analytes that were of trace concentrations were difficult to analyze. So based on that, other methods had to be developed. Method like spectroscopy had to be developed, and then this made it possible to quantitatively analyze samples that have analytes of trace concentrations. So that was the essence of developing spectroscopy. So spectroscopy is a collective term that is used for analytical techniques that is based on the interaction of light and matter. Is a term that is used for the analytical techniques that is based on the interaction of light and matter. So spectroscopy is a branch of spectrometry. It's a branch of spectrometry. Sorry, I have to admit people. So this is a branch of spectrometry. I'm admitting people, sorry about that. So it investigates the absorption, is investigating the absorption of the different substances between the wavelength limit of 190 nanometer and 780 nanometers. So spectrometry is used for both qualitative and quantitative investigations of samples. What I mean by that is used for both identifying if the analyte is in the sample and also quantifying how much analyte is in the sample. So we see here electromagnetic spectrum, because this is important, because it's what we're using. Remember, we said it's interaction between light and matter. So we have to understand the light that is interacting with our samples. Sorry about that. So this is the electromagnetic spectrum. As you can see, this is a light that has increasing wavelength. You can see, and the different rays at the different wavelengths. See the gamma rays, the X-ray, ultraviolet, infrared, and so on. And then between the ultraviolet and the infrared, you have the visible light, the range of 400 to 700 nanometers. So just have that in mind. And so let's see actually the interaction of electromagnetic radiation with matter. So spectrophotometric methods measure extent of the reaction, extent of the interaction. Sorry, I was interrupted by your colleagues trying to admit them in. So it measures the extent of the interaction between matter and electromagnetic radiation. That is what the spectrophotometric method measures. So the extent of the interaction depends on the concentration of the analyte. Analyte is usually available in two forms. It's either in the atomic form of it or in the molecular form of it. And so the interaction between analyte and electromagnetic radiation are in three forms. It's either absorption of the radiation, or emission of the radiation, or fluorescence. So let's look at the three types, looking at the absorption. So in this case, a beam of electromagnetic radiation passes through the sample, and atoms absorb radiation and then transfers the electrons from the ground level state, to the excited state. I'm still admitting people. Okay. Then for the emission radiation, energy is absorbed from the thermal source, which you will see soon, before giving out the radiation. That is, thermally excited atom or molecule returns to the ground state by emitting radiation. Then the third one is the fluorescence. Here, the analyte absorbs electromagnetic radiation to become excited, then returns to the ground state by giving out that radiation. That is, it re-emits the absorbed radiation. You might be wondering, what's the difference between emission of radiation and fluorescence? Sorry, let me just admit people here. Okay. So let's see what's the difference. So emission of radiation refers to the general process of any releasing energy, general process of any releasing energy in the form of electromagnetic waves. Whereas fluorescence is a specific type of emission where a substance absorbs light at one wavelength and then re-emit it at a different wavelength. Absorbs light at one wavelength and re-emit it at a longer wavelength almost immediately after the excitation, meaning that it occurs when the excitation source is present. So essentially, fluorescence is a specific form of radiation emission. Remember, I said radiation emission is a general process of any object releasing energy in the form of electromagnetic waves. Then fluorescence is a type of radiation emission, but this one is different because it will absorb light in a particular wavelength and emit it at a longer wavelength, different from the wavelength at which the light was absorbed. So, and then this leads to re-emission at different energy level. Shown you example here of emission: hot stove emitting infrared radiation, fluorescence, light bulb where the phosphor coating absorbs ultraviolet light from the gas discharge and then emits visible light. See different wavelengths. I showed you the wavelengths when we started, where we have the ultraviolet light, and then when we have where we have the visible. So this one absorbs at the ultraviolet light, absorbs ultraviolet light at a different wavelength, and then emits visible light at the visible range of the wavelength. Okay, so you can see the difference here. Now, let's see the different interactions between matter and the light. This is one is molecular absorption spectrophotometry. One is molecular absorption spectrophotometry. The other one is molecular emission spectrophotometry. Then we have molecular fluorescence spectrophotometry. So you'll be able to, I know you should be able to remember this very well because we talked of the three types: emission, absorption, emission, and fluorescence. And we say two types: the analytes, they come in two forms: the atomic and molecular. So out of these three absorption methods, we have also the two different molecules. So you have the atomic absorption spectrometry, while you also have molecular absorption spectrometry. And you have the atomic emission spectrophotometry, just like you have that of molecular, and you have atomic fluorescence spectrophotometry, just as you have the molecular fluorescence spectrophotometry. Then let's look at the molecular absorption spectrophotometry. That is where we have the UV visible spectrophotometer that it uses molecular absorption spectrophotometry. Okay. Then the basic component of spectrophotometers, the basic components of spectrophotometers are: one, a source of radiation. You must have a source of radiation. You have a device for selecting the portion of the spectrum which is required. Then you have a sample holder. You have a detector for measuring the extent of the interaction, and you have a readout device for displaying the measured signal. So let's look at them one after the other. The source of electromagnetic radiation must provide output that is both intense and stable in the desired region of the electromagnetic spectrum. So it must produce, the source of the radiation must produce both intense and stable radiation that is desired in a particular electromagnetic spectrum of interest. So the general requirements for the source is that it must be of high intensity, it must be highly stable, it must not have any form of drift, whether short-term drift or long-term drift. It must be relatively cheap and easy to obtain, talking of the source of the light, source of the emission, of the source of the radiation. It must be relatively cheap and easy to obtain. So in molecular absorption spectrometry, what we use as a source of light is tungsten filament and hydrogen. Also, deuterium lamp are used. So as a source of radiation for this method. Now, the spectral selection device. Sorry, spectral selection device. So why do we have to carry out spectral selection? If more than one analyte is absorbing light in that system, then it will be very difficult to carry out the analysis if it is more than one. So what needs to be done is that a particular single wavelength has to be selected such that the analyte is the only absorbing species. So this is the reason for the spectral selection device in that system. So we have different types of selection devices, of spectral selection devices. One is optical filters. Another one is prisms. I believe you have been seeing. If you have not, CHM 332. So we have optical filters, we have prisms, and we have diffraction gratings. So prism and diffraction gratings, they both produce monochromatic radiation. That is the type of radiation with a single wavelength or frequency. And so because they produce monochromatic radiation, they are described as monochromators. So your prism is a monochromator, your diffraction grating is a monochromator. So then we have sample holders. We have sample holders. These devices are what are used to hold the samples in place for absorption of radiation. So, and in molecular spectrophotometric methods, sample holders are cuvettes. That's what we're talking about. We have that cuvette, the one we use in the colorimetric method in that lab, that we put into that colorimeter and put the sample inside. And what we have, it can be of different, made from different materials like glass, quartz, or plastics, and they can come in different shapes and sizes. I don't know, maybe you have come across the one of that we use in a colorimetric analysis. It has a rectangular shape and its length is 1 cm. Okay, so, and then we also have the detectors. These are the ones that measure the degree of absorption of the radiation. Detectors measure how much of absorption of radiation occurs. And the principle of operation of detectors usually involve conversion of photons of radiation into electrical pulses. And then the magnitude of the electrical pulses are measured because they are proportional to the intensity of the photons of radiation. So it's the electrical pulses that are measured by the detectors, and the electrical pulses are proportional to the conversion or to the amount of photons. So there are three main types of detectors. One is barrier layer cells. Second one is phototube. Another one is photomultiplier tube. Now, we have readout device. So the electrical signal that we're talking of, that the detector converted the radiation to, that electrical signal is then the signal that is read by a readout device. So it's converted by the detector into a readout signal, then by the readout device. So it is displayed in more convenient form for the analyst. So the electrical signal is displayed in a more convenient form for the analyst, for the person carrying out the analysis. So examples of readout devices include analog or digital meters, include chart recorders, include computers equipped with digital acquisition boards. Okay. So you look at single beam UV spec. We have what I just described for you. We have the source of radiation. We have monochromator. Let's look at prism, for instance. It's a monochromator. Then we have a sample holder, talking of the cuvette. The light passes from this, the light comes from the source, like a deuterium lamp, to the prism, to the cuvette, to the detector, and then it is the signal is seen there by the readouts. At the readouts, get the signal there. Okay. Now, how does it operate? Talking of molecular absorption spectrophotometry. How does it, that is the MAS, how does it operate? Just like I've explained, absorbance value. Sorry, I think I skipped one. I skipped one. I skipped one, okay. So how does it operate? When the instrument is operational, what happens is that the source emits radiation, and this radiation that is emitted is channeled directly to the monochromator. You saw the schematic representation I just gave to you now. So then the monochromator converts the radiation into a monochromatic one, that is one particular wavelength, single wavelength. And then you have the analytes in the sample, usually present as a solution. It's in solution form. And then that solution absorbs the radiation. The unabsorbed intensity of the radiation is transmitted in the direction of the detector. So that means you must know how much light came in, the incident radiation, and you must not know how much light went out, so you'll be able to know the difference. That's the transmitted radiation. So detector then converts the intensity of radiation reaching it into electrical signals proportional to the magnitude, the electrical signal that is proportional to the magnitude of the intensity of the radiation. And then that signal is passed to the readout, where it's converted to a readable absorbance value. So what you will see is the absorbance value at the readout. Okay, so the absorbance value represents a comparison of the incidence radiation, that is IO, and the transmitted radiation, that is IT. So this means that two measurements need to be done. Two measurements need to be done, the incident radiation and the transmitted radiation. So to get the value of the incident radiation, a refractive liquid such as water is first placed in the sample cell. And since there is no absorption, then the radiation, incident radiation and the transmitted radiation is the same, they equal each other. So the value of the incident radiation is kept in the memory of the detector. Then you now empty the water which you used, put with the water that you just used in the cuvette. You empty the cuvette and now put in your sample into that same sample cell. It's the cuvette that you call in the sample cell. And then you measure the value of the transmitted radiation. So if there's a voltage fluctuation between the measurements, those two measurements, incident radiation and transmission radiation, if there's any fluctuation, then there's an error. So there must not be any fluctuation. So what is done to avoid this fluctuation is that two values have to be measured simultaneously. That is, the two values, the incident radiation and the transmitted radiation, must be measured simultaneously so as to reduce reduces to reduce the time of measurement to microseconds. So almost simultaneously, the measurements of the two are carried out. And then to achieve this, you have to use a double beam molecular absorption spectrophotometer. So let's see the double beam. So the double beam is a sketch of that MS. You have the source, you have the monochromator, and then you have the sample there that is analyzed at the same, and where you have the measurement of the transmittant radiation transmission, and then you have the blank here. You also have the incident radiation measured. You have the double beam, the two beams there, and then the mirror both on those sides. Now you have the detector there, so everything comes out there at the detector to where you have the signal processor. So the two measurements are carried out almost simultaneously, just within microseconds. So what are the advantages of the double beam instrumentation? So the instrument, the double beam instrument, it minimizes absorption errors. Like I mentioned, minimizes absorption errors. There's no need to warm the lamp before use. It uses less time for the analysis. The double beam instruments are more versatile than single beam instruments, being useful for both quantitative and qualitative analysis. And though they are so useful, but they are, however, more expensive than the single beam instrument. So just let me know when you want me to stop. I will stop, but I'm just trying to see how much we can catch up here. So this spectrophotometry analysis, this quantitative analysis, is based on the principle of Lambert's law, which states that a decrease in the power or a decrease in the intensity of monochromatic radiation is proportional to the amount of absorbing species in that path and the intensity of the incident radiation. So that is given by this relationship A is equal to ECL, where A is the absorbance and the E is extinction coefficient is a constant, C is the concentration, L is the pathway. In this case, is the length of the cuvette, and then mostly we use 1 cm. So this is just showing what happens. The incident radiation gets into the system where you have your analytes that will absorb the ray or the radiation, and then the one that is not absorbed, the transmitted one, comes out. So I've already described that the incident radiation is IO, then IT is the transmitted radiation, C is concentration, L is the path length. Sorry, the path length you can see here, between from here to here, from this beginning to this end, that is the pathway. So, and that's where we get this relationship. The line IO over IT is equal to KCL. So your this is the same as log to base 10 IO over IT is equal to KCL over 2.303. 2.303 is just a conversion factor. And so your log to base 10 of IO over IT is what is known as absorbance A. So that's how you have this whole thing as A is equal to AECL. So then ECL, A equals ECL is Bell-Lambert's law. So also you can use this log to base 10 of IO over IT is equal to ECL, which is the same thing as A is equal to ECL. So then that gives you log to base 10 of T. T is a transmission, is equal to minus ECL. You just follow this relationship and you end up with A is equal to log to base 10 of 1 over transmission. That is what you have. So because this relationship is important. We're going to see if you can see, hold on a bit, I don't know. So we can see how we can use this to calculate. We use the two relationships. A is equal to ECL, can use that for calibration and also for the knowing the concentration of your analytes. And you can also use this other A is equal to log to base 10 of 1 over T. So the direct method, what are the applications of MAS? That is using Beer-Lambert's law to quantify quantitative, to carry out quantitative analysis. So direct method is one. This involves the direct application of equation A is equal to ECL. So let's look at this example here. You have a solution that has, you're given the molar absorptivity of that solution to be 2 dm cube per mole per cm at 800 nanometer, that's at that wavelength. So if a solution of the sample in a 1 cm cuvette gave the transmittance of 80%, calculate the concentration of the sample in the solution. So this is the calculation. You use that relationship of A is equal to log to base 10 of 1 over T. Remember the transmittance is 80%. So that is same as 0.8. So you now get your A to be 0.09.
Our class is ending 3. Put on my...
Hello? Hello? Do you want me to stop here? Who is the person speaking? Okay. So, yes, you want me to stop here? Okay, give me a few minutes. So, we have the A is equal to ACL. So you now put in your A is 0.097. Your E is given to you as 2. And your C is what you're looking for. And your L is given to you as a path length, which is 1 cm. So from that, you can calculate your C as seen here. I believe it is very clear. You can also use this Beer-Lambert's law also as a calibration method. So in this case, you use this equation A is equal to ECL. It depends on what you're given and what you're asked. Then you will know which of the two equations you're supposed to use. Which of the two relations you're supposed to use. So in this case, you use A is equal to ECL. E is constant. Then L can be kept constant by using the same sample cell, which is 1 cm. So A is equal to KCL. We can therefore plot a graph of A against C, a graph of absorption against concentration. And normally you will have a straight line graph. So, and this is called the calibration curve or calibration graph. As you can see here, the absorption versus concentration. Remember the absorption, the light that is absorbed, it is depending on the concentration of the analyte. The more the concentration, the more the absorption. So, and what are the absorbing species? What are the absorbing species? These are species which absorb radiation in the UV visible region. I showed you the UV visible region between 400 and 700. So one of such species is the organic compounds, particularly those containing unsaturated bonds like alkenes, alkynes, carbonyl compounds, so on. So the electrons in the double or triple bonds are very, very mobile, and so they absorb energy within the UV region to undergo that electronic transitions that we're talking of. Another absorbing species is transition metals and inner transition metal compounds. These ones form colored compounds by absorbing radiation. We also have charge transfer complexes, which involves the formation of complexes with charged ligands, such as cyanide ions and the thiocyanate ions. These have very high molar absorptivity. Okay. So now I think we just talked of, you look at the second one that we say they have to form colored compounds. So in this case, let's look at this equipment that we use for such. So colorimetry is part of the spectrophotometry. So in this colorimetry, the color formation reaction must be specific. So these are the criteria. 2, there must be a proportional relationship between the intensity of the color formed and the concentration of the analyte. 3, the color solution formed, I will stop in the next 5 minutes. Color solution form must be stable for a reasonable length of time, say at least 30 minutes, to allow the analysis to be carried out. The solution form must be clear. It must not be turbid at all. It must not contain suspended particles. And the color formation reaction must be sensitive. That means with a little concentration of an analyte, there must be color generated by adding a reagent. So you look at this, deviation from Beer-Lambert's law could occur. Deviation 1 is high concentration. So the concentration of the solution where you have the analyte must be low concentration. So deviation is high concentration. Also, the use of non-monochromatic radiation is also another thing that can cause radiation, because you must have a single wavelength where that analyte can absorb radiation, and that not many things are there. You don't just have, so if you don't, you must have a monochromatic radiation. So the use of non-monochromatic radiation brings error and deviation. Another one is turbid solution. So the solution must be clear. Otherwise, these are all deviations. So what are the advantages of UV spectrophotometry? It has a wide applicability. Even organic substances and inorganic substances, even such as metals, non-metals, and ions, can be determined by this method. An analytes which do not absorb radiation may be determined by reacting a reagent to produce a product which absorbs radiation. So you see, it has a very wide application. It has good sensitivity. It's good selectivity also, and sometimes specificity. The accuracy is high, and it is very easy to operate. That's the end of the lecture. Thank you for holding on. So we've concluded my own part of the lecture. So, and I will send, as usual,